All right, the unit that we will begin today, continuing Unit 9, we are doing Topic 3, Growth and Decay Models. So what are some situations that you can model with an exponential growth and then with an exponential decay model? So this formula right here is actually two different formulas in one. So when a real life quantity increases or decreases by a fixed percent each year, the amount in of the quantity after t years can be modeled by these two equations. A is your initial amount. So that's your starting number, whatever you start with, however many you start with. The R here is your rate of increase or decrease, and it's usually given as a percent, but you need to convert it to a decimal. The exponent is your time, and usually it's in years, but it can be other increments or other time periods. Now, from last week, we talked about the base. This entire thing would be your base, and it's either your growth or decay factor. It's the entire base. To get the R value, it's either adding or subtracting 1 to it. To 1, you add for above 1 growth, and then to get the decay, you need it to be less than 1, so you would subtract. All right, and then N or Y, whatever you want to call this is your total amount. This is the amount you have after t years. So that's usually what we're trying to find. All right, so I'll do example 1, and then you can do example 2 with your group, checking your answers. I'll do example 3, and then you can do example 4 with your group. So looking at 1, so I'll do these 3, and then I'll move it to the bottom ones because we're going to need to look at the graph for that one. So in the last 12 years, an initial population of 38 buffalo in a state park grew about 7%. So first, we want to know, is it a growth or decay? So this thing says that it grew, so I know it has to be a growth, which means I want to use the growth model, y equals a times 1 plus r to the t, not the decay one. All right, A is your initial amount. So how many you start with? We started with 38 buffalo. So 38 is going to be the A. And for my percentage, 7% as a decimal, we would just move it back twice, multiplying it by 100, makes it 0.07. So making our equation, y equals, or n equals, either way, 38 is the initial population, and we do 1 plus, since it's growth. R is 0.07, so we want to add 0.07 to it. And because it's asking for an equation, we're going to leave t as t. We'll plug in a number for t down here, but right here is just the equation. So our equation is 38 times 1.07 to the t power. Now for B and C, we're actually going to use the model to answer some questions. So for part B, we want to use this equation to estimate how many buffalo were in the state park after 7 years. 7 is giving us time, so we're going to plug in 7 for the exponent. So 38 times 1.07 to the 7th power. So now grab your calculators, and we want to do, just enter that in the calculator, 38 times 1.07 to the 7th power. And we get that decimal, 61.096, but we're talking about buffalo here, so we just round it to the nearest one. We say approximately 61 buffalo. Right, so y, unless it's cents, I mean, if it's money, we can round it to 2 decimal places. But when we're talking about population, we'll round it to the nearest whole number. All right, so part C, we're going to need to use our calculator to find So use the graphing calculator to sketch the graph and estimate the year when there were about 53 buffalo. So what we're going to do here is we're going to take our equation and plug it into y1. So our equation was 38 times 1.07 to the x. And in y2, we want to plug in the number that it wants. So here we plug in 53. So going to the calculator and the y equals, we're going to do 38 times 1.07 to the x power. And then here we're going to do 53. Oops, 53. Now I give you the graph over here, not because I need exact points, but because this actually gives you the window you want to use. So if you go to window, the number here, this is your x-axis. So this is your x minimum. You can't even see that. So x minimum here. So x min. And then the number over here is your x max. And scale is what it counts by. So I want to start at 0, go to 10, count by ones. And then the y min is here. So y min. And then the y max is up here. So then we go 0 to 100. If we go one above it, 100. And what is this one counting by? This one's counting by 20s. So I go by 20s. The scale is 20s. And then if we graph it, I mean, I'm just going to sketch that out. I'm not going to make it exact. But there's our 53. So 20, 40, 50s in the middle. Kind of a horizontal line there. And then our equation starts off at 38, close to 40. And then it's going to go up. Okay. So we're trying to find this point right here. Now this one's not exact. We're going to find it exactly over here. So if we remember how to find the intersection in the calculator, I'm going to write it down here. You do second, trace, and then it's number 5 to calculate the intersect. So second trace number 5 is the intersect one. And then we can just do enter, because they each only have one piece. So enter 3 times. So enter times 3. So then we get that x is 4.917. I'll just put 4.92. And this is years. Now, again, we can round it to 5 years. That would be fine. But if we can find the exact, we can always round. But just because you can round doesn't mean you can find the exact. So I want to practice finding the exact here. And then if it says round to whatever the decimal is, we just round to that number. All right, so go ahead and read number 2. Figure out those numbers and make your equation. And then I'll show the screen in just a second that has all those answers.